tuned in again for the last session of today, which is about the ECO2Fuel project, the youngest and also the largest project from this workshop. And today we will be hearing from Joost Helsen and Pieterjan Debergh two presentations about the ECO2Fuel project. And we will be starting with Joost Helsen. Joost has a background in chemical engineering and is project manager at VITO. He has over 20 years experience in technology development and coordinates large projects focusing on electrochemical carbon capture and utilization. His objective is to bring technology from the lab to the scale that is industrially relevant, meanwhile solving inevitable problems that occur along the way. And he will be telling or giving a presentation today about low temperature CO2 reduction to carbonaceous fuels, design to realization. Joost, the floor is yours.
Thank you very much, Juan, for this introduction. Good afternoon, everyone. I will be taking you on a little journey where, let's say, we move from a very small scale, like we see in the previous presentations, also before noon, towards an industrial scale, or let's say a demonstration scale at least. And I would be taking the opportunity to introduce and to further explain the two projects that were mentioned already quite a bit, so the Lotercom and the ECO2Fuel as examples. Many of the pictures that I will show are from the Lotercom, but I will also, of course, explain on the ECO2Fuel upscaling. So if you can move to slide 2. There, I would like to say that, the evolution of a new technology ideally starts with an idea or a concept that is tested or proved in a lab at a small scale. Typically, initial testing of a catalyst materials is done at millimeter square scale of electrode in very small reactors with only just a few milliliters of liquids, electrolytes. And once a positive proof of concept has been achieved, that is the start actually, or can be the start of an upscaling trajectory, which is what we are limitations here. Basically, only the catalyst species at that point still are under study. And generally, the focus in the lab lies mainly on activity and selectivity of the catalysts. If we upscale and we want to demonstrate the technology, also, of course, the stability will play a role, a large role in that. The first step in this upscaling process, and you can see in the picture, the different stages are depicted there. The first step is to step to slightly larger electrodes in let's say order of magnitude 10 square centimeters, and work in flow cell chemistry. And these are basically miniature versions of the final electrode design, and already give a better impression of the performance of the catalyst in combination with a set of, at that moment, maybe still partially optimized parameters. But for example, flow dynamics can be studied more in detail, and continuous operation is also possible in that, let's say, first upscaled version in the lab. This also enables let's say, the first preliminary aging phenomena that can be studied in this early development stage. Because at this point, first assumptions toward productivity and selectivity can also be made. Gradually, and then we move on to the right, of course, larger cells will be used and more complexity can be added to the system. Electrodes are developed for very specific purposes and in all sorts of shapes. For example, you can have gas diffusion electrodes where specifically the aim is to increase the activity in the three-phase area. And then finally, a full-scale single cell is designed and tested, and increasing that cell from the lab, from this millimeter square or centimeters square to a full scale single cell can be quite challenging and gives rise to a whole new set of problems. Flow distribution, current distribution, structural integrity of cells, gas management, water management, all these play a very important role in large cells. And this behavior can be quite different from what is known in a small cell from the lab. So when a successful large cell design is completed, then this can be multiplied and stacked. Basically, stacking is putting together many single cells to each other and connecting the fluids, inlets and outlets of each cell in parallel. And with this stacking, you can either do this in a monopolar way or in a bipolar way, which is more common in industrial designs, where connecting this cell can be either done in series, in a bipolar stack, or in parallel. The large stack basically is the motor of the process, the motor of the electrolyzer system, and should still be equipped with a lot of peripherals. And this is what we call the balance of plant. This was also what I will discuss in this presentation. In Lotercom, we have scaled up to approximately 5 kilowatts, so from the lab to 5 kilowatt installation. I will discuss a lot of it today in the presentation. And in ECO2Fuel, we will start from this 5 kilowatt plant and make 2 steps from 5 to 50 kilowatt and eventually to 1 megawatt system. Slide 3, please. So where to start? I have indicated 3 main points which are important in the upscaling process, and that's the first, the process flow diagram, secondly, the single cell and stack design, and finally, the balance of plant. Slide 4, please. So for the process flow diagram, we should set the boundary conditions, and these are defined by the small scale experiments and adding some margins, for example, cell voltage, Faraday efficiencies, current density, which are derived from the lab scale conditions. And then we can add some process specifications, like whether we want to have the process developed in a 2 or a 3 compartment system, which type of membrane should we use, which type of electrolyte should we use, what is the governing pressure and temperature that is most beneficial for the process to operate at. And then finally, we also need to construct mass and energy balances, having kind of an energy input, CO2 input, conversion rates, heat dissipation. All these things need to be calculated in, let's say, a black box simplified model. Concerning the process of CO2 electron reduction, there's 2 main configurations that are used, and you can see them in the top right picture. The left one is the gas diffusion electrodes used in combination with both a liquid analyte and catalyte. So CO2 gas is supplied through a gas diffusion electrodes, and it's then contacted with the liquid electrolyte at the membrane surface, at the cathode surface, where electrocatalysts are present to catalyze the reaction. On the right side, you see the system or the configuration that is used also in Lotercom and in ECO2Fuel, which is the humidified CO2 process, where CO2 is first humidified or mixed with water vapor, and then added to the electrolytic cell. So in this case, we have a 2-phase electrolytic cell or stack. On the one side, we have humidified CO2, and on the other side, we have the anolyte, which is, in our case, alkaline solution of potassium hydroxide. Slide 5, please. So this would be then the process flow diagram for Lotercom. But similarly, a process flow diagram for ECO2Fuel can be calculated based on the increased scale, of course. So what we see, we have a certain flow rate of CO2, demineralized water for humidification of the CO2. We have a 1 molar KOH supply towards the stack. Voltage and current are also indicated here in this picture that are needed to convert basically the CO2 to the carbonaceous fuels. And of course, in the outlet, we have both gaseous products and liquid products, and also heat. And of course, this is also important to notice that for partially the energy that is used for the stack for the process is partially converted into heat as well. Slide 6, please. So once we have this basic mass balances process flow diagram, we can start designing a single cell and stack. Slide 7, please. And what's important here in stack design, actually a lot of things are important, but I will, let's say, strike upon a few of them at least. And one of the main things is the cell flow characteristics. Optimizing the flow inside the compartments of each cell is extremely important, of course, for having a good distribution of, first of all, CO2, but also, for example, have a good evacuation of gases that are being formed, like hydrogen and oxygen, which are always present as well. So the optimal gas and liquid flow should be maintained in the compartments because the gas and liquid fraction strongly affects the overall cell resistance. And therefore we should avoid building up of too much gas inside the compartments. Another thing that's important to take into account into the stack design are the specifications from the MEA, which is the membrane electrode assembly, which is basically one piece of material that contains both the membrane and both electrodes. These specifications are very much governing also the type of cell and stack that can be designed. And then, of course, whether you want to choose for a bi or a monopolar stack design. So the bipolar stack design uses bipolar plates and only 2 external electrical terminals where the voltage is, the stack voltage is then applied to and is distributed across the bipolar plates. Another important aspect aspect is the aspect ratio, which is the ratio of the height to the width of the stack, as this will determine the residence time and the flow distribution as well inside the stack. The picture on the right that you see is an exploded view of the Lotercom stack as it was designed and constructed. And there you can see the structural plate in the bluish greenish color, and also the bipolar plates. The membranes are indicated, and all these cells combined is what we call a stack. In this case, it's a 10 cell stack. So we have 10 anodes, 10 cathodes combined in one big stack. Another point, especially here in Lotercom and ECO2Fuel, is the pressure, since we want to operate the process under elevated pressure. we are subject to the European PE directive. So that's the Pressure Equipment Directive. And this, yeah, also complicates things a lot, because you need a lot of certification and yeah, calculations basically on the stack itself. Slide 8. On the stack design, one of the things that still maybe sometimes are overlooked are the occurrence of parasitic currents. And to explain this, I indicated in the blue arrows actually the existence of these parasitic currents. So the green arrow indicates, let's say, the main current that should be transported through the active area of the cell, so through the electrodes. But since we have liquid, at least on one side, liquid flow in one compartment in the anolyte, there is a connection, direct connection between the bipolar plates from one end to the other. So there is like, let's say, a salt bridge between different bipolar plates at different potential, giving rise to parasitic currents. These are actually ionic currents that occur and can partially decrease the efficiency of the system. So this needs to be taken into account during the stack design to make sure that these are limited. And this can be done basically by two means, either by creating a high resistance of the electrolyte, for example, by lowering the conductivity, but that's not always possible, of course, or by reducing the section of the liquid flow channels, let's say. Another important thing during stack design is the pressure drop in the compartment. This should always be taken into account, because pressure drops, especially pressure drops across the two compartments, anode and cathode, is something to avoid. Of course, compartment thickness also plays a role to have as much, as a compact design. You should have very thin structural plates, and of course also the mechanical stability of the total system is quite important, next to the sealing. I will talk about this a little bit more. So mechanical stability for the Loader-Com stack, as you see here, we did some finite element analysis on the stresses that occur during pressurizing during the process itself, and at design pressure of 16 bars, and also during heating up of the system. And what is shown here is just areas where potential exceeding of let's say the material properties, long-term properties could occur, and these need to be taken into account, of course, in the design. But this gives us a way to change the design and adapt it to make sure that it complies with the specifications. Of course, sealing, if you work with pressurized stacks, it's even more important. Basically, two types of sealing exists. We have O-ring sealing, which is, I think, known, and also flat gasket sealing. We can use different types of material specific to what is needed in case in contact with the chemicals that are being produced, for example, or the pH conditions of the process. To give you an idea, this is the Loader-Com stack, and during the pressure test. So as I mentioned, we have to comply with the PE directive, which means that the stack as such needs to be tested at a pressure which is approximately 1.5 times the design pressure. In this case, it was 24 bars. As you can see, we did it successfully. Next to this pressure testing, also a manual and an EC conformity needs to be in place in order to have this stack even operating at an industrial site. So these are things that you don't need to consider as much as in a lab, but once you want to upscale, this becomes very important. And slide 12. So finally, I want to discuss with you the peripherals, the balance of plant, which is basically the surroundings of the stack being the heart of the installation. Okay, we go to slide 13. The starting point when designing or when devising this balance of plant is the PFD, so the process flow diagram that I showed in the beginning. And after some iterations, you come up with a final, what we call PNID, which is a process and instrumentation diagram. On this PNID, we need to do an initial hazard analysis. This is very important to maintain a safe way of working. So every component needs to be checked in relation to the other to make sure that all the hazards that occur in this balance of plant can be managed. Then after this initial hazard analysis, there is a list of components needs to be made. So this means sizing the components that they have the right dimensions, selecting different manufacturers, types of instrumentation, for example. And then there is a purchase process, which is also quite evident, but still a very lengthy and tedious process. When we have all the equipment available, we start with a container layout. This is in the background. You can see the loader container in our production hall where it was constructed. And ideally, you would then have a layout so that the construction can proceed swiftly, and it's known where to put which equipment, of course. So after construction, there is still a final HAZOP based on the as-built PNID. And also a manual and EC conformity. All these things need to be in check before we can proceed to the certification. And finally, the FAT, which is the factory acceptance test, and a site acceptance test, SAT, at the premises. So a few more words on the PNID. So this is the example of the Lotercom PNID, where you see all the actually the different components, instrumentation, valves, pumps, tanks are given here, and also the connections and specifications on diameters of tubing, etc., etc. So this needs to be prepared before any purchase even can occur or happen of the process. We have, in short, we have in the blue circle, the stack, of course, which was discussed before. The red is the Catalite tank, red circle, and the green circle is the Analyte tank. And in yellow is the Catalite loop given, and in a green marked is the Analyte loop. The purple circle indicates the analyzer, so we can actually analyze all the gases that are produced on the cathode, and I mean all the main gases like CO, ethylene, hydrogen, of course, CO2, oxygen. These are measured in the analyzer. And also, it's not just for process follow-up, but also as a safety feature for detecting any mixing of oxygen and hydrogen in both tanks. If we go to slide 15, we can see the container layout, so how it was designed and drawn before the construction, and some pictures of the finalized room. So we have the ATEX room, which is the picture on the right, referring to the right part of the container. And then the top left is the control room where the electrical cabinet and the PLC is located. Bottom right is what we call a wet room, where also the compressor is and the supply of dimming water and KOH tanks are located. If you go to slide 16. 16 is then a visualization of the process control, the automation actually that is developed for Lotercom project. And as you can see, this is very similar to the PN idea, and this indicates also all the values of the most important transmitters, level transmitter, pressure, temperature, connectivity, and also the indicators on the stack, so the voltage and the current which are going through the stack, and also the pressure regulation of the stack, because pressure regulation on the stack, especially at higher pressure, is quite challenging. We use dense membranes and there is no pressure balancing between the tanks. So all relies basically on the good differential pressurement between anode and cathode, and also the control of the release valves of anolyte and catalyte tank. A lot of safety measures have been taken to ensure that the system shuts down in the event of an oxygen transfer, for example, to the cathode side. We always work with a slight overpressure towards the cathode because we are continuously monitoring the cathode gases. And then if in the event of for example, membrane rupture, we can immediately see any oxygen transfer occur in the gas analysis. Okay, I think for, let's say towards the end of the presentation, just a few more pictures of the pilot with the view. These are in slide 17. These are the views of the ATEX room, so the explosive-proof room in the loader container. And the red circle indicates the tank 1. As you can see, this is a 25-liter tank. The blue circle indicates the position where the stack should go, and we'll see later how it's installed there. On the green is the tank 2, which is the anode anolyte tank containing mostly oxygen, of course. If we go to slide 18, you can see the finalization at our demonstration hall where the pilot was actually built and putting it to the crane. And slide 19, you can see when it was installed, but that's already shown, I think, in the video as well, at RWE next to the cooling tower. And on the right side, you can see the stack with the blue circle, which actually is installed at that moment inside the container. Slide 20, I would like to say special thanks to my colleagues, Rob, Hans, Diane, Jeff, and Pete, and Philippe, for their great work, because without them, this would never have been possible. So finally, what's next? ECO2Fuel, which is basically the whole procedure and workflow as I explained during this presentation. And in the first step, we will design a 50 kilowatt stack, and they should be ready by next year, September. And we will, of course, also have a balance of plant to host this stack ready, and that will be by October 2023 next year. And then a few months later, we will start the campaign so that we can still finish before the midterm of ECO2Fuel and having, let's say the first results of the improved catalysts and membrane electrode assemblies tested in our new 50 kilowatt system. Okay, thank you. This is was all for me.
Thank you, Joost. Thanks a lot filling us into this design of the system. Next, as a presenter, we have Pieterjan Debergh. Pieterjan holds degrees in bioengineering and economics from the University of Leuven and is a researcher at VITO. He focuses on techno-economic assessment in the field of CCU and bio-based economy. The objective of his research is to evaluate the economic feasibility of early stage technologies compared with the conventional technology and to identify key points to focus in future research. So today we are going to hear a presentation from Pieterjan, which is called The Economic and Environmental Aspects of Electrochemical CO2 Conversion to Carbon Neutral Fuels and Chemicals. Pieterjan, the floor is yours.
Thank you, Siobhan, and also a good afternoon to everybody from my side. So indeed, our work is focused on understanding economic feasibility and also the environmental integrity of new technologies. And that is what we have applied here to the context of CO2 conversion to several products. The ECO2Fuel project is, of course, very young still. A lot of analysis planned, but we also have quite some other material already from the Loader project, for example, that we would like to present today. Slide 2, please. So the way we usually approach this is to make a model of the system that we're looking at. So basically modeling what goes in terms of mass, what goes out, what is the energy consumption involved. And then for each part of the process, we will start associating costs to it, so CapEx, OpEx, and of course also environmental impacts, trying to build really full value chains, also including downstream processing, for example. And we make our models dynamic so that we can always do a proper sensitivity analysis, which is key of course, for such exercises. Slide 3, please. So the overall process scheme, we may have seen it today already a bit, but I would like to take the economic angle here. Because indeed there are some technologies, well, at least for methanol, available that can use CO2 as a feedstock. However, these involve typically first separate hydrogen production from a water electrolyzer. And then afterwards, this hydrogen is combined with CO2 in a hydrogenation plant, which runs at high temperature and also pressure. What we try to do here is, of course, to reduce the cost of such a process. And one obvious way to do that is to think about process integration. And that is exactly what we aim here to do. So we integrate those steps, and we have a new type of electrolyzer that can use directly CO2 and water as input. And also very important is that it can, this is a more flexible process because it's not such high temperature, so we can more easily vary the output. And well, the analysis that I will show focuses on methanol as product, but the technology has the potential also for other alcohols to be produced, which are sometimes also higher value, so that's also very relevant to note. Slide 4, please. So a critical question when looking at the economic side is what is going to be the cost of this new type of electrolyzer that we're building. And I think that we can have some quite relevant insights from a conventional water electrolyzer, which is not the same, but conceptually fairly similar. And here in this analysis, you see basically that two things are quite important. So that's the scale and also the volume. And with scale, I'll mean that, for example, here, the 1 megawatt system for a given production rate will be always much cheaper than the smaller 200 kilowatt system. But also the amount of systems that are produced, which you see going from left to right on the horizontal axis, that also has a very big impact. And that is also what we see today with cost of hydrogen, of water electrolyzers already coming down compared to what we saw in the past. And we think and we hope that the same would also apply to a CO2 electrolyzer. This will be a bit more expensive than a conventional water electrolyzer because there's a second input stream. But we do believe that a range of 400 to 600 euro per kilowatt should be feasible in the longer term. Slide 5, please. So how does the cost structure of a CCU pathway look like? So here we have an example in the graph to the left. And there you immediately see a lot of green. That's electricity cost, which is well known that that is a critical factor. That the left bar basically assumes continuous operation at an historical typical price of 50 euro per megawatt hour, which is what a large industrial company would pay when it is running base load from the grid. However, we have a very high interest to try to run the electrolyzer on a dedicated renewable energy supply for two reasons. Of course, from an environmental point of view, this is much better, but also from an economic point of view, this can be interesting. Because the renewable energy prices have come down over the past years, you see some price ranges in the graph to the right. In some cases, even below 30 euro per megawatt hour. However, when we try to run on renewables, it's going to be very difficult to do that in a baseload continuous manner. So we have taken here a flexible scenario which we only have 4,000 operating hours per year, so only half basically. But in return, we get a lower electricity price, and you see that this indeed is an economically interesting approach. Hence also the attempts in this project to have an electrolyzer that is really the load following capability so that we can really follow this strategy. Slide 6, please. One also important point of the exercise is to look at the influence of the electrolyzer performance and where it needs to be in order to be competitive with a certain benchmark. And in the colored lines in this graph, you see different cell potentials, which is the energy you need basically to get the reaction running at a sufficient rate. And you see that this really has a big influence, of course. We also note that the first horizontal line that achieving the historical price of methanol, of course, is very, very challenging. You always need very affordable electricity for that. The current market prices of ethanol are, of course, already more elevated, and there's inflation everywhere. But probably, and that's the top horizontal line, the first market could be to use it as a renewable fuel, because in that market we are competing with other clean fuels, and we can typically get a somewhat higher price range. Other business cases could also be, for example, to use those fuels for peak power energy production. That's also covered. Slide 7, please. Then we also need to think about the environmental impact. And to do so, we need to map all the impacts along the value chain. So here, for example, the process is assumed to run exclusively on renewables, and more specifically here I have assumed onshore wind. That wind turbine will require a certain amount of steel and other metals to be manufactured. We also have a number of consumables in the process, and then of course in the heart of the reaction we have the stack, and you see a picture of the stack below. You see that there is copper involved there is nickel involved there. So all those material uses we have mapped and obtained data from databases like ECO2Fuel, where you can find all this, in order also to make the comparison with classical fossil-based methanol. Slide 8. On this slide, you see in the table to the right all the different impact categories that can be considered. So in ECO2Fuel, there's even about 20 of them. Here I have made a selection. Obviously, we're very interested in the global warming potential, but there's also quite a number of others that are also relevant to consider. And in the graph to the left, you see the contribution of each point in the process and each material to the overall environmental impact. And on the top of this graph, you see a lot of dark blue color, which is the electricity. So even though we have assumed here that renewable electricity is the energy source, it is still a very important environmental impact factor, as you see. And this is something that we see quite consistently in the literature. If you would take a picture for a green hydrogen, for example, produced with electrolysis, you would actually get a fairly similar picture. But electricity is not all that matters. You also see that some of the metals, and then I'm talking specifically about the nickel and the copper, that also have a very measurable impact, for example, in the categories in the middle, like acidification and ecotoxicity. Hence also the importance of the project to deal efficiently with metals. And one way to do that is for starters to have a productive system. We're talking about current densities, that is important. Thinking about appropriate material use, also in the design phase, definitely avoiding rare earth materials, because these are even more energy intensive to extract, so that is all to be taken on board. And then we go to slide 9. So we're obviously interested to see how the CO2-based methanol that we're producing together with renewable energy as input, how that would compare to the fossil-based version. Fossil-based methanol is typically derived from natural gas. Natural gas is turned into syngas and then syngas into methanol, usually in very, very big plants, 500,000 tons per year. So that is the benchmark. And when we look at the first category, we see that the pathway with the recycled CO2 and renewable energy indeed has a drastically lower global warming potential than the case of the natural gas-based methanol. And this is from a cradle-to-grave perspective, where we would assume it to be used as a fuel. In other words, the embedded carbon being released again in both cases at the end of life. There's also other options possible if it would be used in a product and this product would have a long lifetime, then the carbon can also potentially be stored for a longer period. But we also see that there are a number of other indicators where the CO2-based pathway has the advantage, but not necessarily all of them. For example, LOP, that's land use, that's quite intuitive to understand that there is a disadvantage. But also some others where we note that the fossil-based pathway can be better in some cases, which is again why it is also not only for the economic perspective, but also for the environmental perspective, quite important to have an efficient system, energy efficient system, but also efficient in terms of material use, which is also why in the project we are thinking very much about the materials that we use and also the recycling. That we have electrodes and catalysts that can be recycled, and that is also a very important channel through which we can actually lower the environmental impact. So this work is ongoing. I'll just go to slide 10 just to say thank you. This is ongoing work. We have the ECO2Fuel project ahead of us, where we will have no data about also larger scale operations, which is very relevant to the economic part, also about the material use, etc., energy use, which is also important for the environmental part. So happy to engage in any discussions about this, either in the Q&A or also afterwards, so feel free to contact us. So that was it from my side for now.
Thank you, Pieterjan. So we still have 15 minutes to discuss the question of the ECO2Fuel session. Then we have 30 minutes to discuss the question in general, which are still not answered. So I would like to start with a question for Joost Ramato from DTU. He asks, how does the significance role of the membrane separators change as we scale up the cell in these projects? For example, in terms for the voltage or products and ion crossover.
Schwan, can you repeat the question? Because I was hearing only part of it.
Oh, okay. So Ramato from DTU asks, how does the significance role of the membranes separators change as we scale up the cell in these projects? For example, in terms of voltage or product or ion crossover?
That's a very broad question, I would say, because it can change in many different directions. Generally speaking, for example, in terms of membrane thickness, thinner membranes support the use of higher currents in the sense that they are more conductive. Of course, in systems like Lothar and ECO2Fuel, we use dense membranes, which means that they are not separators as we see, for example, in water electrolysis, but it's more a dense membrane, which does not have any pores inside, let's say, and where the only thing that's transported are ions. So we have ionic transport through the membrane. There, normally, we do not see significant transmission of products from one side to the other, although there is some co-transport always possible. So together with, for example, hydroxide ions, also other components can be co-transported. So there's a lot of investigation also needed there to characterize membranes in terms of performance, which is basically conductivity and selectivity, and then making sure that this still is in line with the targets.
Thank you, Joost. Professor Reinhold from Helsen, Germany, he asks actually two questions, and I don't know who of you would be more appropriate to take the question. So the question is, when it comes to commercial scale, how sensitive are the requirements to gas purity? And the second question is, you mentioned 60 bar pressure. How big is the pressure impact to the process?
Okay, I think I will take this. So the impact of the pressure on the scale of the system, right? Or
so the question says, if we are targeting now the second questions, you mentioned 60 bar pressure. How big is the pressure impact to the process?
Well, that's still under investigation to see how elevating pressures actually should yield higher productivity. So we expect and we foresee also that increasing the CO2 pressure on the cathode side will in fact also increase the productivity, since more molecules of CO2 are available for reduction. But still needs to be validated in the pilot scale. And the first part of the question, maybe.
So when it comes to commercial scale, how sensitive are the requirements to gas purity? Which I think depends always on the applications you want to have the products for, right?
Yeah, indeed. Our main focus now is still on quite high purity CO2 streams. We are still, let's say, in the early days of developing this process, and we want to focus really on performance based on CO2 with high purity. But once this is certainly in a next stage, and I think ECO2Fuel will therefore very much be providing answers, will be to check the influence indeed of impurities in CO2 streams, and also checking what is what are the range of side products that are being formed.
Thank you, Joost. I believe this is a question for Pieterjan. Somebody asked, apart from fuels, alcohols, what other markets can we tackle with this technology?
Yeah, I think that there's a number of products that we can think of. In principle, the process can be steered towards different products. Some of them are, let's say, smaller or relatively small, like formic acid, which was already mentioned also in the other session, which is a small base chemical, but with a high value. So that is very interesting from the perspective of reaching competitiveness without relying too much on subsidies, etc., or on too much on scale. But then there's also very, very large markets. I think, for example, ethylene is a molecule that there's increasingly a lot of attention going to. And when you think about it, actually a fairly large share of the overall basic chemicals market could be covered, which I think is also an asset for the technology, that it is relevant for many different products. And in fact, sometimes you will have the case where it will actually, like ECO2Fuel, but also other cases where it will be producing multiple products at the same time, which is not necessarily a problem as long as the DSP and the separation allows for it, and it can actually be not necessarily a problem. But I think that is really an asset also for the technology, in the sense that it creates a critical mass, so it's relevant for multiple products. And that also will help to for the technology to mature and to receive a certain scale in terms of manufacturing, etc., which is very important, I think.
Thank you. Another question, I guess, also directed towards you. Can you provide more detail on which factors determine the climate impact of the electrochemical CO2 utilization products?
Yeah, that is a good question, because it depends on a number of factors. But as a very general rule, I would say that whenever we recycle CO2 from a certain source, and we use renewable energy to do the recycling, and we use that product to displace a fossil-based product, then generally there will be a climate benefit. So the emissions, overall speaking, will be lower than in the benchmark case where we did not do this. But some other aspects are relevant as well. So first of all, where is the CO2 coming from? If this is a cement factory or a natural gas power plant, okay, this is from a fossil origin still, the carbon. And if the carbon is then released afterwards, then we still have the emission of fossil carbon, of course, in the end, even though we have less carbon emissions than in the benchmark case. If, on the other hand, we have the CO2 is coming from a biogenic source, for example, from biogas, or even it is extracted directly from the air, which sounds maybe a little bit like far future, but there's also a lot of work ongoing in that area. Then, of course, it can be climate neutral as a whole, or even when this carbon taken from the air or from biomass is stored for a longer period in the product, then we can even talk about negative emissions. So it's important to keep the distinction in mind, indeed.
Thank you. So one last question before we come to the wrap-up session, and I believe you both could answer this actually. You mentioned energy efficiency as one important aspect for the industrial implementation of the technology. What other aspects are relevant?
Shall I start?
Sure.
Well, I think we talk a lot indeed about energy efficiency. There's also the productivity of the system that is critical. I have a lot of output from a certain amount of surface and material. But then there's also the stability. So you need to know that a conventional water electrolyzer will have well, the stack, the heart of the reactor, will have a lifetime of a few years, typically 5 if you use it continuously. So after that period, you'll have to replace it because the performance is not satisfactory anymore. Here in this case, we'll also have to envisage maybe not exactly the same lifetime, but also a system that is sufficiently stable. Because from an economic point of view, if you have to replace all these valuable materials too frequently, that is of course not going to work. But I think that is also an element that is very explicitly included in the ECO2Fuel project. So maybe Joost wants to elaborate on that.
Well, maybe I can just add one important thing I think for industrial application is robustness, not only for from the catalyst or MEA side, let's say, but the entire system, and also ease of operation is quite important. So the more complicated processes, installations, the more difficult the road to industrialization is, I think.
Thank you. And one last question, which is coming in right now. Sarah from France is asking, what do you expect the financial benefit per ton of methanol and I believe also alcohols of the direct conversion versus hydrogenation of CO2 can be?
That is something that we're looking at. So we have also data, let's say, about the conventional approach, the two-step approach. I think what will be making a difference, it's difficult to put a number on it here and now, but I think what is, from economic point of view, very important is that we have this flexibility and also that we can lower the pressure of the system compared to the conventional approach, which is above 70 bar or even 100 bar, and that is typically something that is quite costly. But in my honest opinion, the biggest benefit will be the integration with renewables. As you saw in my slides, this really has a big impact if we can reduce electricity cost by coupling it directly, even though we have somewhat less operating hours for the electrolyzer, then we still can have a clear financial benefit, which was in my example more than 100 euro per ton compared to the conventional CCU approach. But yeah, this is something that clearly we also need to work out in more detail also in ECO2Fuel.
Thank you, Pieterjan. Just in time. So thanks again to you, Pieterjan, and to Joost for giving this presentation on ECO2Fuel, a very exciting project. I'm very, very grateful to be working with you and the 13 other partners in this project. And I would like to use the opportunity now to switch to the wrap-up session and bring first the questions of the ocean project, which we could not answer before. And there are many, so I get to it. Which technical challenges do you expect in upscaling this technology to higher TRL? So this question goes to Arno or to Professor Santi.
Well, maybe I can just start and then Arno can add more. I think that there are still problems in terms to extend more the lifetime of this system. And so, as I mentioned, we have up to now results up to 100 hours, which is still not enough. Of course, it is necessary to extend more and probably to optimize also the system to go in this direction, and also tend to integrate all the different elements. Up to now is still let me say, the first part, which is the production of formic acid. What we need is to integrate with all the other elements and to arrive to, let me say, higher TRL level by integration of all the elements. Arno?
Yeah, so what I want to add is, so in, let's say, the ocean demonstrator, we're using bipolar membranes, and these membranes are, well, limited in their current density. So out of my head, you can go up to 80 milliamps per square centimeter. This limits the amount, or it will increase the amount of cells that you need to meet a certain production rate. So therefore, it will make it more costly. So that is definitely something that needs to be, well, investigated and further developed. But another point is, yeah, we also need to, let's say, increase, let's say, the product concentration to, let's say, avoid a lot of downstream separation costs. And yeah, I mean, if you now run at, let's say, 5 or 8%, I mean, if you can bump it up to, well, 20 or 25 or 8%, I mean, that would help a lot. So these kind of things are, yeah, I think, really important to investigate as well.
Thank you. Mr. Vivikan Tan from Essen, he asks, how is the efficiency of the nanotube titanium oxide structure compared to the disordered titanium oxide structure?
Sorry, the comparison between the titanium oxide nanotubes and
the disordered titanium oxide structure.
Well, simply the disorder is much less efficient. But as I mentioned, is not the titanium nanotubes itself, but is, let me say, very small debris of disordered titanium oxide, which is on the top of these titanium nanotubes and strongly anchored with them. So if we remove these and or if we support or another type of titanium, then there is a drastic drop in the performance and also inter-redox property. So it's this kind of interaction which is critical.
Thank you. Another question from Messina. How to increase the formate yield compared to carbonaceous products, in particular gas products like CO? Is it mainly a matter of catalyst composition or electrolyte structure or operation conditions?
Well, is a combination because, of course, one of the main problem is how to realize a perfectly uniform electrode, especially when you go to a large scale. And of course, when you have inhomogeneities in let me say, electrical distribution, into electrode and so into potential, then this is one of the sources why you can decrease. In optimal conditions, the performance can be up to over 90, 93, 94%, which can be also a bit increased more, but you are already at the limit. Of course, it's a bit less when you go to large electrodes. And so this can be obtained by, well, improving essentially the design and the preparation of the electrode. However, the main problem is that, as mentioned before, what is the target is to arrive to even higher current density of this electrode, which is still is good, but still not enough, should be improved. And in this condition, when you increase more the electron, the current density, there is a drop in the selectivity. So up to now is a compromise between current density and optimal selectivity.
Thank you. Another question asks about glycerol. So glycerol is used as feedstock for the anodic reaction. Can also other feedstocks be used?
Yes, of course. Initially, the idea was to have different, for example, to use glucose and other. Then the decision was that was better to use a kind of side product to form some product in order to increase the efficiency in forming it. Of course, there is a choice in terms of anodic reaction which can be made. The advantage in this case is that if you form some product, then also you have not only increase in terms of performance, in terms of efficiency, but also a reduction in the cost of separation. But yes, glycerol is one possibility you can also form, because essentially you can also have other molecules which can be converted to form it. So this was a choice because at the end now is relatively not a very costly product, but yes, can be also some other possibilities.
Thank you. And I believe Arno just mentioned before that the bipolar membranes can only operate at 80 milliamps per square centimeter. So here comes the next question. Can you say which energy efficiency is obtained for formate producing, for example, at 100 ampere per square centimeter, or which is the operating cell voltage at this current density?
Yeah, so what we've let's say done in the Ocean project is, so we run it at between 100 and 150 milliamps per square centimeter, and in general we don't measure the let's say the half cell potential using a reference electrode, but if you look at the entire cell, we're between 4 to 5 volts, so that's where we operate, and we achieve close to 90% Faraday yield, which is really good. But we're say you can try to increase it even further, but I think it's more important to look at the long-term stability. So how does it operate after 100 hours or 400 hours. And also when you do have a unexpected, let's say, shutdown, and you start up again, you want to go back to the same level again. And we've seen the same with the catalyst with our catalyst, that if we restart after a shutdown, that we go back to the same level of efficiencies as before. I think we're quite happy with that.
That's very good. So it can recover. So it is actually capable of being directly connected to PV or wind. Very nice. So one last question of the ocean project, which is always very important. The demonstrator produces formate. What is formate good for?
What is useful to formate?
Yes, yes.
Well, as mentioned, this is a formate we are using. We transform to oxalic acid, and then we are reducing to form glycolic acid, which is a monomer for polymerization. This is now the general scheme. Of course, we have tested also direct conversion of CO2 to oxalate to oxalic acid, but it's still not competitive for now. So it's still better to have an electrocatalytic formation and then thermal steps of formation of oxalic acid. But as I mentioned, oxalic acid is just intermediate, and the final product is the one that I mentioned. I think that in terms of added values, this is a very good monomer for polymerization, and you have values of the product which is now much higher than the cost of the process, so which make quite competitive this synthesis with respect to commercial production.
Thank you, Gabriele. So there are still other questions. I'm going to shoot them. I believe they are now with respect to Lottecom. So one goes like, is there a strategy to make the catalyst more selective so that you have higher efficiencies?
If I can answer to this question, we in the ECO2Fuel project, we are using atomistic simulation in order to understand the doping agents of cuprite in order to make the reaction more selective towards specific products. So this is an ongoing activity, but especially on the ECO2Fuel project, because the Lotter project was now approaching the end with the demonstration of the co-electrolysis plant.
Thank you, Antonino. Another question is, which other materials do you consider for O2 evolution reaction and iridium ruthenium oxide? Because this catalyst is quite expensive. So maybe I can already start to say that whether in Lottecom nor in ECO2Fuel we use iridium ruthenium oxide. We know that iridium ruthenium oxide can be used for water electrolyzers, but we are not using this. We are using only nickel-based electrocatalyst for the oxygen side. Another question for Lottecom, I believe, would be, or maybe for ECO2Fuel and for Ocean, would be, who do you think has the best starting position for the commercialization of electrochemical CO2 conversion? Asia, Europe, or USA? And I know, in fact, that there are two companies, one in Europe. This is called Dioxycle, which is funded by the Breakthrough Energy, which is the foundation of Bill Gates. And there is another company called 12, which is funded by Shell in the US. And these are all companies, these are startups. We are talking today about projects. We know that the ECO2Fuel project has a a funding of 20 million. So that's already a good start. So I would believe with Dioxacycle that Europe is in the forefront of commercialization of the CO2 electrochemical CO2 utilization. But the discussion is open to the others. Maybe you also know other projects and other companies.
Of course, this is an important process that could be commercialized through the world because, you know, carbon tax and green certificates are, of course, important in all countries. So I think that all industries dealing with cement production, with steel production, that are really need to address the increasing cost of carbon certificate would be very strongly interested in this process. This is my personal opinion.
Thank you, Antonino. One question coming in, I believe this is more towards Lotocom and the catalyst development. What is more important for the catalytic effect of copper, the crystallographic surface or the crystallographic defects or impurity atoms?
I guess I have to answer this. But as I mentioned also during the talk, there's still a quite open field of many parameters that influence the catalytic activity, and I would say it's still not clear. There have been discussion that some subsurface oxygen is responsible, that some facets are responsible, and I still read contradictory reports on these facts. So from my point of view, there's no clear answer on this question, but maybe Antonino or others have more clear view. Obviously, we see that if you change the catalyst, there's a difference, but it's still difficult to assign it really to one specific parameters because it's always a play of several parameters at the same time.
Yeah, I would like to add a comment on that because, of course, the overall process is affected by several parameters. That means the catalyst morphology, composition, the type of electrolyte that is used. There is an effect of the dimension of cations on the of the recirculating electrolyte on the carbon dioxide reduction process. And also very important is the electrode structure, the interface between the electrode and the membrane in a zero gap cell. So of course we needed to rationalize all these aspects, otherwise we can really don't see a specific direction to follow. So we need, there is still a lot of work to do in let's say, individuating the most appropriate operating conditions and how these can match with good catalyst formulations. So there is still a long way to go to better understand the carbon dioxide reduction process.
Thank you, Simon and Antonino. So when I'm looking at my watch is 4:48. And the workshop only goes until 5 o'clock. So I would like to use the opportunity to thank first everybody. So I would like to start to thank all participants. I hope that the workshop, that you like the workshop, that we could satisfy your hunger about the electrochemical CO2 utilization, whether you are a scientist from this field or a non-scientist. I also would like to thank or to use the opportunity to thank the European Union for the financial and management support. Special thanks goes out to Søren and Yolanda and Lucia, who have been there today with their statements on the importance of CO2 utilization. Thanks also to the presenter, who did an amazing job to giving a very comprehensive overview of their complex research areas. And last but not least, I want to thank RWE, who organized and hosted this workshop in such difficult times. To all applicants, please feel free to contact us via our social media channels and to communicate with us on social media and stay tuned. And if you have some questions which were not addressed today in the workshop, I would like to ask you to connect with us, send us emails, send us questions, and we will be getting back to you in a very timely manner. So thanks again to everybody. And if there are no comments anymore, I would like to close this workshop. It was a pleasure to be moderating this workshop.